Hello, in this video we'll be discussing the Bohr model of the atom. So throughout the ages of chemistry, several different models have been theorized for what the atom looks like. And the Bohr model is actually not the most recent up-to-date theory of what the atom looks like. So you may wonder, well, if it's not the most up-to-date, then why do we have to learn about it? While it's true that the Bohr model is outdated based on what we know today about the atom, it does help introduce key concepts and understandings that will be important when you talk about what is the most recent understanding of the atom, which is the quantum mechanics model. So the Bohr model will help introduce in a more visual way the concepts and the understandings that you'll talk about when you talk about quantum mechanics later on in the semester. So the Bohr model was theorized and conceptualized by two physicists in the early 1900s, Niels Bohr and Ernest Rutherford. And they theorized that an atom behaves similar to a planet, in that you have a central body, in this case the atom's nucleus, which is then orbited and surrounded by electrons. And these electrons are situated in fixed orbitals called energy levels, similar to how the planets orbit around the sun in fixed orbital patterns. They theorize that electrons, in a similar way, orbit around a central nucleus. The nucleus, of course, is made of protons and neutrons, with the electrons orbiting around them. And so you'll see that I've numbered them 1 through 4, and this is just to give you sort of a visual guide to the energy levels. So you can have n equals 1, n equals 2, n equals 3, n equals 4, and so on. But these are the most basic breakdowns, so that's why I only put up to n equals 4. Because after that it just gets redundant. So n is just shorthand for energy level. So n is just sort of the atomic physics way of denoting energy level. And you'll see that again when you talk about quantum mechanics. So when n equals 1, that's when we're talking about this first ring right here. So this first orbital here. Sometimes you'll see this called a shell, so that you can also call this the first shell. The first shell can hold up to 2 electrons. So 2 electrons is the maximum number that can be put onto this first ring. When n equals 2, that's the second shell out here, the second ring. And on the second energy level, you can have a maximum of 8 electrons. So a maximum of 8 electrons can fit on that second energy level. Now that includes 2, like n equals 1, we can have that 2, but we can add an additional 6. So we can have up to a total of 8. On this third shell, when n equals 3, you can have a total of 18 electrons. So you can have a total of 18 electrons in that third energy level. And that's coming from the 2 plus the 6 plus an additional 10 electrons. On this fourth energy level, on this fourth shell, you can have a total of 32 electrons. So it can house a maximum of 32. The 2 plus the 6 plus the 10 plus an additional 14 for a maximum of 32. So what does all this really mean? Well, what it means is that we can use these electron densities, if you will, these electron housing numbers, if you want to call them that, to place electrons in a Bohr model of an element to show where those electrons sort of exist for that element. So we can draw Bohr models for different elements to show where those electrons are. So to start with an example, let's take oxygen. So let's say we wanted to draw the Bohr model for the oxygen atom. Well, we know that the atomic number of oxygen is 8, which means it has 8 protons. That means it's also going to have 8 electrons, because you have the number of electrons to balance out the number of protons. So for just a regular old oxygen, we have 8 electrons. And using these rules, we want to draw the Bohr model of oxygen. So we know a total of 2 electrons can be placed on that first ring. So there in red, I've drawn the first 2 electrons. And a general rule of thumb when it comes to drawing electrons on a model is that you want to start at the bottom and work your way up. So you want to start at the lowest energy levels and go up higher. So you're sort of subtracting as you add electrons. So on that first ring, we can only add 2 electrons because that's all that it can hold. And then once we fully populate this first ring, only then can we move on to the next ring. And that's true for each ring in the Bohr model. So now that this first ring is full, we still have 6 electrons left, because remember in oxygen we have a total of 8. So we've already put 2, now we have 6 left. And you'll notice that for n equals 2, we can have a total of 8 electrons. Since we only have 6 electrons left to draw, we can draw all 6 remaining on the second ring. So there we are, the remaining 6 electrons for oxygen. So now we have a total of 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 electrons. So I'll just go over that one more time just in case that was a little confusing maybe. You want to draw your electrons starting from the lowest energy level, which is number 1, and work your way out. Keep in mind how many you can hold maximum in each level. So we can only hold 2 in the first level, so we draw the first 2 here, and then for the remaining 6 for oxygen, since the second ring can hold a total of 8, we draw the remaining 6 there. So let's say we wanted to move a little up. So let's say instead of oxygen we wanted to draw the Bohr model for sulfur, which is just one row down. So we want to go straight down the column, and now we want to focus on sulfur. Now sulfur has twice as many electrons. So for sulfur, we're going to fill up the first shell, we're going to fill up the second shell, and we'll move on to the third shell. And to save you from drawing all those electrons, you can really just write the number of electrons for each shell. So like I said, we have a total for sulfur, we have a total of 16 electrons that we have to account for. We're going to start from the bottom and work our way out. So we start with the first shell. We can have a total of 2 electrons in the first shell, so we're going to fill that up. For the second shell, we can have a total of 8, and we're going to fill that up. So now we have 10 electrons that we filled. 16 in total, so we have 6 left to account for. And we're going to stick the remaining 6 out here in the third energy level. So we filled up the first 2, we're left with 6, so we stick the 6 where we have them left. And to check your answer, to sort of check and see where you're at, just add them up. 2 plus 8 plus 6 equals 16. All of our electrons are accounted for. And that's how you can sort of go about drawing these Bohr models of different elements by assigning each shell its electrons in order, starting from the lowest, working up to the highest. So one thing I would like to point out is that you do have splits in shells. So see how in the third and fourth energy levels we can have a total of either 18 or 32 electrons? Well, the thing about electrons is that they repel one another. Electrons are all negatively charged. So if you get a bunch of them together in one shell, they'll start to push each other away. So naturally, the electrons will start to sort of segregate themselves. They'll sort of start to kind of diverge from each other into separate subshells. So for n equals 3, for this third ring out here, you'll start to see sort of a splitting happen where you'll end up with one half of it having 8 and one half having 10. So that third energy level is sort of going to split in half, where 8 is on the first half and 10 is on the second half. And again, that's because those electrons are sort of repelling one another. 18 is just a little too much, so they sort of naturally segregate. That way they don't overwhelm each other. And that same thing happens for when you get out to n equals 4. So notice how we have this 32 electrons. That's just way too many electrons for one shell to actually handle. So the shell sort of naturally segregates into 3 suborbitals, where you have the 8, the 10, and then the additional 14 sort of segregate out on their own. So this is sort of the shell splitting that you'll see. So when you populate your electrons, I would keep this in mind. And so one last thing, and this is sort of leaping a little bit into quantum mechanics, but I think it's important to sort of understand at this point. So where do these numbers actually come from? The 2, the 6, the 10, the 14, the 8? Well, they're coming from the positions on the periodic table. So the 2 in the first shell is coming from these elements here, where you have these 2 columns here plus helium up here, and those represent where the 2 comes from. The 6 is going to come from these elements over here. You'll notice that if you go across the row here, you have 1, 2, 3, 4, 5, 6. So 6 in total going across. And so these elements over here represent where that 6 is coming from. If you add the 2 and the 6, you get the 8, and that's where the 8 comes from. You're adding the 2 from this column, these 2 columns here, plus the 6 from this group over here. The 10 is coming from these elements, this group of elements here, the transition metals. If you count across from scandium to zinc and so forth for each of the other rows, you get a total of 10. So that's where those 10 electrons come from. Add up the 2, the 6, and the 10, you get a total of 18, which is where that 18 here comes from. And finally, so for n equals 4, you'll notice that we have the 2, the 6, the 10, and then the additional 14. With those 14 electrons at the end come from these elements here. The F block, as it's known in quantum mechanics, but if you count across, it's a total of 14 elements, which is where that 14 at the end comes from. Add them all up together, you get that total of 32. But like I said, for n equals 3 and n equals 4, those orbitals will sort of split because electrons repel one another. And you're not going to really cram that many electrons into one orbital without them doing that splitting. So hopefully that wasn't too confusing. I'm sorry if it wasn't as straightforward as it could be. It's kind of hard to talk about atomic models because they're so intricate and they're so sort of detailed. So I hope that cleared up any kind of questions you might have had about the Bohr model.